Okay, welcome to the next lecture in our series on nutrients and agroecology. So this is on soil biology and fertility, again as a part of our SD 3100 Principles of Agroecology class. Just as a reminder, there will be a short quiz upon As You Learn after this. Okay, so let's just, I'm going to start by kind of going over what objectives are today and then kind of place this lecture in the context of our other lectures, right? So our objectives for today are to understand nutrient cycling and its role in soil fertility. And second is to understand the role of microbial ecology in decomposition and nutrient cycling. So our last two lectures are kind of focused on needs of nutrients in plants and photosynthesis. And our next lectures are going to look at kind of different ways of managing soil fertility in kind of natural systems and traditional agroecosystems and kind of more modern, kind of appropriate, more sustainable agroecosystems. And so this is kind of just diving one step deeper into the biology of what's going on here. And so nutrient cycling is really the process by which organic matter is decomposed and makes nutrients that are embodied in that organic matter, makes it available for plants to grow again. So it's kind of think of it as the cycling of nitrogen, phosphorus, and other nutrients through an ecosystem. So you can think about this if we're going to visualize it. Where is this happening? One of the easiest places to envision it is in a compost bin. And this isn't a great one, but you can see here on the left, there's organic matter that's been put in. There's some you can see some decomposed organic matter, some that's already there. But we can also visualize in other ways. On the lower right is a large scale pile of compost that's what somebody's checking the temperature to make sure it's getting the right temperature for decomposition to occur. And in the upper right is a roller crimper, and so this is ryegrass that has been planted with the intention of kind of bending it over and cutting it so that those nutrients can be made available for other crops. And so this is kind of a strategy for both it's a cover cropping strategy that's used to both recycle nutrients and suppress weeds. And so we're kind of going in that direction to think about what are the different strategies for doing it. But again, what we want to think about today is in all of these settings, where are the microbes? What are they doing? And then what's the kind of system by which kind of ecologically that nutrients are made available to plants? And again, we want to try to kind of mirror or echo what natural systems do when we think about designing agroecosystems. Okay, so nutrient cycles. So on the left, we have a picture of a tropical rainforest. And in many ways, tropical rainforests are kind of famous for adding to our understanding of nutrient cycling, because tropical forests look incredibly lush. You would think there must be so much kind of fertility in the soil here, but typically tropical forests exist on relatively degraded soils. They're not nutrient-rich soils normally, but the forests are able to grow really kind of in lush ways because they're effective in cycling nutrients through them, right? So when I think about it, there aren't a lot of nutrients in the soil, but there's a lot of nutrients that are flowing through the soil, right? So when I think about this process of nutrient cycling as a really important part of that. For this, a lot of the graphs or the figures that I'm using come from The Ecology of Ecosystems, which is a book by John Vandermeer. John Vandermeer, just as an aside, is an ecologist by training. He's kind of really a world-renowned ecologist, but he also kind of thinks a lot and writes a lot about the political ecology of agroecosystems as well. So he's kind of a radical ecologist in many ways, but a wonderful writer and wonderful thinker about agroecosystems and about kind of ecosystem functioning. Okay, so we start with thinking about a process for nutrient cycling. How do we conceptualize it? Again, if you want to go back up for a second, we just visualize this picture of a forest, like where are the nutrients cycling, where are they moving? And we can think about this as really starting from kind of mineral parent material, right? So where does it come from to begin with? Where does the phosphorus come from in particular? Well, it starts from mineral parent material, so the weathering of rock that's in place, which typically leads to kind of ions in the soil. So these are kind of available chemically charged chemicals that can be in solution, right? So they're essentially dissolved and suspended in the water, the bits of water they're in that are in the soil solution. That gets taken up by plants, absorbed by plants. Again, this works primarily for, think of this for phosphorus in particular, but also it's slightly different for nitrogen, but also the other macro and micronutrients. So it's taken up by plants. It's then plants die or lose their leaves, so there's decomposition. You can see, kind of imagine that happening in the forest floor in that tropical system. But also those ions that are in the soil solution are also being immobilized by microorganisms, right? They're being taken up by bacteria, by small arthropods, so small insects. So they're being immobilized by fungi as well. So they're being taken up not just by the plants, but by small microorganisms. Those also decompose. Both of those, the decomposition, both of those results in soil organic matter, which then puts those nutrients, the ions of those nutrients, back into the soil. The kind of complexity to this, that's the normal cycle, but also those ions or those nutrients that are in the soil solution can also be adsorbed to soil colloids. And what that means is it gets essentially kind of glommed onto, locked onto, almost like magnetically held, chemically held actually, onto clay and other soil particles. So it gets essentially immobilized, so locked up in the soil itself. And the second thing is it can be leached out of a system, right? So in a healthy natural ecosystem, we want this cycle to be capturing as much as possible. And we want there to be a balanced flow of nutrients kind of into and out of soil colloids so that you get this movement, right? This movement is what is fueling the plants. Plants don't have to hang out to those nutrients forever. They will accumulate some over time, but really its growth depends on the flow, this flow of nutrients. And when you have low stocks or availability of those nutrients, you need this flow to work, and you need to avoid having leaching out of the system, right? So we can think about this, and again, I want you to think back for a second to that tropical system and imagine this happening for the different nutrients within it. So think a little bit, one step kind of deeper on how plants take up nutrients in that kind of one of that second part of this nutrient cycle. So how do they get it? There really are kind of three ways that plants kind of take up or get those nutrients. The first is root interception. And this is where roots essentially grow in ways to find those nutrients, right? So it's the roots finding the nutrients. And so they're looking for it. And they have ways of trying to figure out where is it, kind of putting out feelers or scouts almost to figure out where those nutrients are. The second one is mass flow, and this is where nutrients are dissolved in the soil solution, the water that's in the soil, and they're moving, that water is moving and the nutrients are moving through the soil to the rhizosphere. And the rhizosphere is really this area right around the roots and the root hairs. So you can imagine this isn't the roots growing to find the nutrients, this is the nutrients in water moving to find the roots. Not that they know what they're looking for, but they're just moving. And the last one is diffusion. And so this is where soluble nutrients move through the soil water to get to the roots. Now, you want to think about this a little bit. Why is mass flow different than diffusion? So mass flow is when the water, nutrients are in the soil water and they're moving. The water is moving. Diffusion is when the nutrients are in the soil water, but the nutrients are moving within the water to find the roots. And the fastest method, the fastest kind of movement is mass flow. Diffusion is slow, and obviously root interception can be quite slow as well because you're relying on the roots to grow into those places. For different nutrients, these mechanisms have different levels of importance. And so just to point out for nitrogen, mass flow is the most important. That's the way the majority of nitrogen is kind of acquired, at least for maize plants, that's the majority of it. For phosphorus, it's through diffusion. Similarly for potassium, it's through diffusion, but you can see for other nutrients, it's through mass flow as well. And for most of them, root interception can play a role, but not as big of a role. So again, you just want to think about how is it getting it. This is how it's moving through that solution. Okay, now don't get too worried about the graph on the right, which kind of shows molecularly what's happening when nutrients are taken up by plant hairs. And the main thing I want you to be thinking about in this is just to visualize. On the left, we've got root hairs on a corn seedling. So imagine that there's a root and there are these tiny hairs. And obviously we kind of know that those hairs are really important because they increase the surface area of the root, and they become the sites. All of that surface area of those little hairs on the left become the sites for potential nutrient absorption. And so I just want us to visualize on the right, we see that there's imagine a root hair, and the root hairs are actually kind of putting kind of chemicals. In particular, they're putting out hydrogen ions into the rhizosphere. And so the rhizosphere is this little, imagine this as a kind of a thin area just outside of the root hair, but it's not in the kind of soil matrix itself. It's kind of it's like a kind of, imagine it as like a little slimy surface around the root hair where these chemical reactions are going on. And so the root is, or the root hair is really trying to chemically pry nutrients off of these soil particles, which we see here. And you can imagine some of the nutrients that are being kind of hanging on to or glommed onto either soil particles or even so these could be like clay particles. They could also be organic matter, right? So in the kind of soil matrix, or in the soil, the nutrients hang on to these soil colloids or soil particles, and the root hair tries to essentially get those off. So get some nitrate, get some calcium, get potassium off of these particles, right? So I just want you to be thinking about it's actively trying to essentially to get those particles and transport them into the root hair so the plant can utilize it. Okay. So let's dive a little bit deeper into the nitrogen cycle. And we've already covered the nitrogen cycle a little bit, but hopefully this gives you kind of one more pass, and it should kind of reiterate things that we've talked about before. One of the things I want us to think one step more about is the role of soil microorganisms in kind of a healthy nutrient cycling for nitrogen. So we'll see this kind of the role of the soil organisms as kind of central to this. So it's again one step deeper, and to see also kind of what are the different key processes that are going on. Okay, so let's kind of talk through this. And the first phase of this, which we already have covered, is nitrogen fixation stage. This is where atmospheric nitrogen is converted into an organic form, into ammonia, and then into amino acids. So that's what the rhizobium bacteria, which are in the root nodules in nitrogen fixing plants, so they're taking it and they transform it into ammonia and then into amino acids, and then it's going to be taken up by the plants, right? So the plants then don't worry really about the chemical reactions that are happening here. Again, mostly this is associated with rhizobium bacteria, which is the symbiotic relationship between the bacteria and the plants. Here's some examples of root nodules. I think we've shown one before. Again, these are highly specialized bacteria, which are really, they rely on the carbohydrates that are produced by the plant. In exchange, the plant gets the nitrogen, which is fixed and sequestered by the bacteria. They form these nodules, which are kind of partly inside of the roots themselves and partly on the outside. And then they provide the plants with amino acids, and they get these carbohydrates back, right? So the plant's not absorbing it, it's actually getting an amino acid rather than a nitrate, for instance. In some cases, if you're growing like a bean crop or another nitrogen-fixing crop, you may actually need to inoculate or to essentially kind of put these bacteria into the soil to make sure that they're there and can colonize the roots, right? Okay, so that's our rhizobium. There's other bacteria that can also fix nitrogen. So cyanobacteria and azolla ferns are other examples. And these are actually really important in rice culture as well. So it's not just nitrogen fixing bacteria, but there are some actual cyanobacteria and in association with ferns can also fix nitrogen. So that's another kind of example of nitrogen fixation. Okay, so if we go back to our nitrogen cycle, one of the key processes I want you to be thinking about, so we've got the plants take it up, plants die, and they go through a decomposition process, and we're going to come back to decomposition in a little bit. Decomposition obviously is being driven by or kind of moderated by soil microorganisms, which are eating, breaking things down. So it creates organic matter. Organic matter is not something that can be automatically taken up by plants. So there's nutrients in that organic matter, but the plants can't absorb it as it is. It has to go through a process called mineralization so that it transforms into a form that plants can take up, right? And so this process of mineralization, so breaking down of the organic compounds which include the nitrogen, is done by through mineralization, and it results in it's a very specialized bacteria, and it results in nitrogen in the form of ammonium. Okay, NH4 plus. You don't have to remember this, but just try it. It's great if you can remember that this is ammonium, and that this is one of the forms of nitrogen after mineralization, right? That ammonium can be taken up by soil organisms themselves, so they need the nitrogen themselves, so they take it up. And it also can be broken down further into nitrates through nitrification. It takes again these longer. I think what else I want to say about this? The breakdown of these. This process requires energy from the bacteria itself, right? So the bacteria need energy to be able to break this down. Okay. Next part of the process I want us to think about is nitrification, and this makes the nitrogen into a form that's even more accessible to plants as nitrate. So it's the conversion of ammonium to nitrate, and there's really actually two separate conversions that happen in this process. Requiring different bacteria. So that's, you don't need to remember which those bacteria are, but it's just important to know that soil microorganisms are important for this process of nitrification, which again makes the nitrogen available in a form that can be absorbed by the plants, absorbed by the plants. It's interesting to note that this process actually gives off energy, so this locking up kind of releases energy that the microorganisms can use themselves. So you can think about this ammonium as actually having some embodied energy, like it's a fuel, and so this is a switch. But it's also interesting that the process switches the charge, it's from a positive charge to a negative charge, which makes it easier for the plants to absorb the nitrogen from this. Okay. All right. So the next part, obviously, we've kind of talked a little bit about is the process of absorption, right? So plants can take up nitrogen as ammonium or as nitrates. There's trade-offs though, depending on what they do. So nitrate, if they take up plants as nitrate requires more energy to use. So it requires more energy. It's an anion, so it's a negatively charged particle, and it's less likely to be held in the soil. So nitrate is more likely to be dissolved into the soil solution and leached away, right? So it's the ammonium can be toxic to plants and can't be stored for a long period of time. So there are trade-offs between whether the plant takes up and absorbs the nitrogen from nitrate or from ammonium, but essentially it can do either one of those. In general, crops are more efficient at taking up nitrate. That's just, there's more, there's more volume of nitrate that can be absorbed through nitrate. And so that tends to be what it is. Even if we apply an ammonium or ammonia fertilizer, it gets transformed into nitrate in order to be taken up by plants. Okay. So one other process, when I think about these other processes, one is denitrification. And this is the loss of soil nitrogen to the atmosphere through its conversion back into N2, which is atmospheric nitrogen. And this also happens through soil microorganisms. And as people who've taken Laura's Science for Sustainability class will kind of remember this, this often happens in places that are either waterlogged or in stream beds. There's certain conditions that promote denitrification and this release. And if you think about this from a nitrogen cycling point of view, we want to minimize this. We want to minimize the loss to atmospheric nitrogen. There's other consequences in terms of greenhouse gases from doing this, but because nitrogen is our limiting nutrient, we'd much rather have it be absorbed in the system. We don't want it to be lost because this is again often our limiting nutrient in terrestrial ecosystems and in terrestrial agroecosystems. Again, one of the intermediate processes in denitrification is the production of nitrous oxide, which is a greenhouse gas. If we put too much nitrogen into the system, then we get too much nitrate, and that can promote denitrification. Okay. All right. The last part again is another loss of nitrogen in the system that we want to be concerned with. Now, this is a process that doesn't require soil microorganisms, but is leaching. And I think we've briefly mentioned this in the past, but this is the loss of soluble nutrients to groundwater. And so this is essentially where the nitrate is in solution or the ammonium is in solution, and they can be, as the water that's in the soil percolates down into the groundwater, the nitrogen goes with it. And if we put too much nitrogen in, it's actually, the groundwater can become contaminated by nitrates, which can have health consequences for people who drink that water. Again, both nitrates and ammonium are highly soluble, and they're easily leached. If nitrogen is either over-applied or poorly timed at a time when plants don't need or are taking up the nitrogen, that nitrogen is easily leached into the system, right? So I want you to think, try to visualize back to that tropical system, which is typically a nitrogen-poor system, but it remains a lush and productive system because of robust nitrogen cycling. That essentially this cycle of fixation, which brings nitrogen into a system, and this part of the system, which is taking it, the plant nitrogen through decomposition, organic matter, ammonium and nitrates are taken back up either by organisms or by plants. If this system is robust and denitrification is low and leaching is low, then a system can be more productive, right? So in conventional agriculture, we want to make sure there's always enough nitrogen, and so we often over-apply. It's estimated that only about 10% of the nitrogen that's applied as fertilizer is actually absorbed by the plants. The rest is either lost through leaching or through denitrification, right, which has its own set of consequences. So we're going to think about how do we emulate more of a tropical forest system where it's a more closed system. Okay. Again, if we think about nitrogen conventional agriculture, this is the anhydrous ammonia, which is being applied. So this is essentially a compressed, high pressure and high heat liquid form of ammonia, which is injected into the soil. It can't be applied on the surface because it would automatically go into denitrification. It's going to be injected into the soil, and it's so that's one way. It comes from the other thing is, the other thing to remember is that in conventional agriculture, we don't rely on fixation by plants. We rely on chemical fixation. where atmospheric nitrogen is converted to ammonia through pressure and heat. Okay, so that's where it comes from in conventional agriculture. You get a high energy using chemical process to do this. So how is it applied? It's either applied as nitrate, it's applied as ammonia, or urea. Those are the most common, the common forms of it. And again, up in the upper right is anhydrous ammonia, which is a pressurized, liquefied form. Kind of think of it as like a propane version of ammonia. These are forms that are readily available to plants, but these are also, in particular, nitrate and ammonia, if they're applied at the wrong time, are lost. And if you think about it too, so this is a cornfield where it's being applied for a new crop, or the residue of a cornfield, but there are no other plants taking up the nutrients that are being put in here, right? So there's nothing. This is kind of the antithesis of our tropical forest system, where if you applied some nitrogen, it would be captured by something else. Here, it's got to be applied to make sure that the plants have the nitrogen they need, but it's also likely to be lost because plants aren't, there aren't many plants there at the moment, right? Okay. Again, the places that are different are that fixation is different. There's more likely denitrification and more likely to have leaching from a system, okay? If we think about the nitrogen system in balance, we want to think about how do we create this balance? We just talked about this recently. We have high demand and high solubility make nitrogen supply and supply a kind of a key balancing act. It's really important for it to be balanced. In conventional agriculture, we rely on applications of nitrogen for it to be available. And so we're putting more into the system rather than balancing. In sustainable agroecosystems, we really want to find this balance that minimizes that balances mineralization and absorption. So we're trying to really increase the amount of organic nitrogen that's released, and so that mineralization can be balanced with absorption, right? So that we're not putting so much ammonium or nitrates into the system that it has to leach. We want to have the kind of entry be kind of proportional to the absorption. Okay, let's think a little bit about some organic nitrogen forms. There's a lot of common ones that are used in organic inorganic agriculture. Feather meal is one, so this is actually ground up kind of feathers from chicken. And after each one of these organic nitrogen sources is the content of the fertilizer. So fertilizer content is often expressed as the amount of N, P, and K. So feather meal has 12% by weight nitrogen, 0 phosphorus, 0 potassium, right? So that's the N, P, and K, and those numbers represent the percent by weight for N, P, and K. Worm castings, which are below, have much lower amounts of nitrogen per se, but they actually bring other organic matter with it. Poultry manure, which you can see in the bucket in the kind of foreground, has both nitrogen, phosphorus, and sometimes potassium as well, but quite wide of a range. Blood meal, which is, you see a bag of blood meal on the right. Blood meal is kind of exactly what you expect it to be. It's actually typically dried, ground cow blood from kind of slaughter operations. You can imagine this being a common source in kind of small scale diversified agriculture, but right now most blood meal is produced by kind of from large, as a byproduct of large scale livestock production. Fish emulsion, which is up in the middle, this is now if you buy fish emulsion, it wouldn't look like this, but this is how to make your own fish emulsion. And again, it's one of the things that if you buy fish emulsion, keep in mind that this is typically coming from operations that are quite a ways away, and that those operations themselves have a lot of energy and environmental consequences embedded within them. But it's a very nutrient-rich source. So these are kind of some of the different kind of typical sources of nitrogen. Okay, so let's think about phosphorus, right? So phosphorus has a similar cycle. Again, phosphorus is critical for plant flowering, fruiting, and root development. Unlike nitrogen, there are no natural inputs. We don't have a corollary to fixation for phosphorus. Kind of the system has what it has. You can apply phosphorus that exists in other places, but we can't, there's no natural process for kind of fixing it. So what you have is kind of what you get. It moves through the system in a similar way. So we're going to kind of think about what's that cycle. But it also has several opportunities where it can get fixed, where it can get locked up, either by soil organisms or kind of in the soil itself, kind of chemically within the soil. So let's kind of walk through this cycle again, trying to visualize what's happening within either a natural ecosystem and what we might want in an agro-ecosystem. So it's primary materials that are kind of the starting point for this. So this is basically the parent material, the parent rock material that's being observed. Its release is essentially moderated by organisms which can make that phosphorus available. So think of this as kind of organisms which are essentially loosening up the phosphorus from the parent material and affecting how much of it is going into kind of soluble phosphorus, right? So in the water of the soil itself, right? The next step is that soluble phosphorus then is taken up by plants. That phosphorus is either eaten by animals, or as the plants die, it can also, and those animals become organic matter, or the plants themselves die and become organic matter, right? So it goes from parent material into this, and then we try to imagine the phosphorus cycling, keeping it cycling through. Okay, so the organic matter is then immobilized by soil microorganisms. So soil microorganisms are going to eat the leftovers of plants and animals, and they incorporate that phosphorus into their own bodies, and it gets locked up until they themselves die, and then it gets released. It gets released as back as soluble phosphorus. That soluble phosphorus, then we get these kind of two balances back and forth here. The soluble phosphorus can get locked up by the organisms, or that soluble phosphorus can get fixed. So this is kind of chemically, not organically, but chemically fixed within the soil. So it gets locked up. It gets kind of glommed on into a form that's not soluble in the water itself. This is really important for phosphorus. And this process is really driven by pH, or the acidity of the soil. Now, again, don't worry too much about the chemical formula at the bottom. Actually, don't worry about it at all for right now. But it just kind of, but it shows, it's easier to look at the graph that's on the right, which shows across the bottom pH, right? So low pH is high acidity, high pH is lower acidity or more alkaline. Kind of remember that each one in a pH scale is actually 10 times as acidic. And what we want to focus on is this part here, this graph, is where is phosphorus relatively available. And it's right around a pH of 6, which we would consider kind of a fairly neutral soil. Slightly acid, actually, kind of 5 to 6 is maybe slightly acid. 7 would be a much more neutral soil. But 5 or 6 would not be uncommon in your kind of soil around here. Most of the soils around here, with a few exceptions, are kind of in the 5 to 6 range. Some are more in the 4 range. And oftentimes, the best way to make phosphorus available is not to add phosphorus. If you've got a soil that has a pH of 4 or 5, you don't want to be adding more phosphorus, because it will become fixed to iron and aluminum. And it can be, so it can in different forms, we'll just say, or it can be locked up with clays. It can in different ways. So what you want to be doing is to change the soil pH. And so a common thing that people do is they'll lime. Lime basically raises the pH of a soil, and it releases, it kind of gets the soil to release phosphates. And you can't really, it'll only go up to being kind of neutral of a pH of 8, but and you don't need it to be that high. You don't even want it to be that high. You want it to kind of just at least get up to this kind of sweet spot of 6, so the phosphorus would become more available over time. But again, even at that, the majority of phosphorus is still locked up in these other forms. right? Okay, one last thing to understand phosphorus, we've talked a little bit about this. We know that the roots are really important. Just like nitrogen benefits from having an association with bacteria, rhizobium bacteria, plants benefit from having associations with mycorrhiza, which are fungus, that help it in particular to get phosphorus. So most plants have an association with fungi that assist in nutrient absorption. You can kind of get an image of it here. You can see the kind of the hazy parts. So if you look at this image of a plant here, you can see the roots and the root hairs, but you'll often see this kind of white fungi growth on roots, and that's not the roots or the root hairs. It's a fungus, which is this functionally extending the reach of the roots. And it's not just extending the reach to absorb, but it actually helps release the phosphorus in the soil. And again, that fungus creates a symbiotic relationship that exchanges nutrients for carbohydrates. That's kind of the evolutionary kind of barter that the fungi and the plant have made. Plant gets nutrients, the fungi get carbohydrates. This really increases the effective root zone, and it creates this network of roots and the kind of fungal mycelia, these kind of hairs that go from it. And again, it's particularly important for phosphorus because the phosphorus is there, but it's locked up. And again, the fungi can actually help kind of unlock it in a way. And some of these are ectomycorrhiza that actually live kind of partially inside of the roots themselves, and so they have a really a relationship that we're just trying to understand. And I have to say this is an area where we are just understanding the complexity of the diversity of soil mycorrhiza and their roles. And so if you imagine, and we're just learning about how specific certain mycorrhiza might be for either for crop plants or for plants in native forests. So if you imagine trying to reforest or restore an area into a natural vegetation, we don't know how land use affects the presence of mycorrhiza, and so these mycorrhiza may play a really important role in the establishment and restoration of natural species. Okay, if we think about different forms of phosphorus management in systems, so again, what happens when it's applied? We want to be thinking about: is it going to be absorbed or is it going to be locked up? If it's too acid of a soil, it might just get locked up. So you're going to think about applying this along with lime. Phosphorus comes from a couple of different forms. The most common is most common organic form is bone meal. So this is essentially just like it sounds, ground up bones, which brings both nitrogen and phosphorus. Or rock phosphate, which is mined deposits of phosphate that are typically mined from areas that have high amounts of deposits of, for instance, shorebirds or bats. So these are kind of fossilized bird or bat poop, if you will, and it's mined. You can think of this as typically rock phosphate is usually considered to be organic in some sense, but it also has some energy use in its mining, in its preparation. Okay. So for both, I want to take a closer look at decomposition, which is driving parts of these different processes, right? So this is back to this nutrient cycling, and so decomposition is this process by which dead plants are converted into soil organic matter. And when we say soil organic matter, we really mean this kind of amorphous organics. We're not thinking about like pieces and chunks of leaves. We're thinking about things that are really kind of decomposed and become part of that kind of richer, darker soil that we'll see, right? So it's the conversion of organic material, like crop residues, into organic matter, this kind of more amorphous carbohydrate molecules. Again, this is critical for production because that it releases. The organic matter also has an ability to kind of chemically hold some of the nutrients that are in a system. We can think about this in different ways. I just wanted an excuse to have a dung beetle in a photo, which is the real reason we can think about this. But you want to think about this as these different systems, right? So we got a plant, and this is kind of our typical kind of trophic levels. We got an herbivore eats the plant, maybe a first carnivore eats that herbivore, a second carnivore eats it. Each of those things, each of these animals and the plants themselves become detritus, this kind of broken down pieces of organic material. And then that is essentially kind of incorporated into decomposers. And those decomposers also become detritus. So there's recycling that's going on between the detritus and the decomposers. But this process of taking the detritus and becoming incorporating the decomposers results in the release of inorganic nutrients. And it's these inorganic nutrients that are being taken up. It's not these organically bound nitrogen or phosphorus. It's these inorganic nutrients that are bound. Okay, we're getting to the end. Thanks for your patience. The other thing I want you to think about is that within organic matter, there are other things other than the nutrients themselves. There's different carbon or carbohydrate chains that lock up nutrients and different things for different periods of time. And so this is a graph showing different types of organic materials that are common in organic material, and the breakdown of these over time. So the simplest are sugars, right? So this is years across the bottom and the percent remaining. So sugars are fully dissolved or broken down within a year time. Within about a half year time, 90%, this means 90, so only 10% of the sugars are remaining. So it gets broken down quite quickly. Hemicellulose, which is a type of cellulose, but it's kind of not as long, lasts a little bit longer. 90% of it is gone after a year, only 10% remain, and by 2 years, most of it's gone. Cellulose takes to think about this as the kind of some of the building blocks for cell walls and plants. After a year, about 22% of it is remaining, but most of it is gone, and it takes about 4 years for the rest of it to go. Waxes take longer. Lignin, which is more common in woody materials, and then phenols, which are kind of also kind of more complex and long-lived organics. Now these are important because we want actually a mix of these different organic compounds or components within organic matter. We want these different pieces to be there because some are more permanent than others, right? So these ones that are more permanent are going to lock things up and release it slowly over time. We don't want everything to be decomposed in a really fast period of time. We want to have a balance of these, right? So you think of this as things that slow down the decomposition process but give us a wider range of materials over time. Almost there. When I think about a couple of just quick processes, comminution is the physical breakdown of organic material into smaller pieces, right? So this is when detritus, so little pieces of organic matter are kind of being broken down into kind of an organic soup. Think of this as just being broken down into smaller pieces. And then catabolism is the chemical breakdown. So the first is the physical breakdown. Think of this as little organisms chewing things up and kind of tearing it up and breaking it up in physically. And then it's chemically broken down, typically by fungi and bacteria, kind of both breaking down. So kind of cutting it up and then chemically breaking it down in catabolism. And it's the catabolism that results in the release of nutrients and humus. And humus is this kind of amorphous organic molecules, so just that are kind of clinging to the soil, clays and colloids. They become part of the soil. Okay. Sorry, we don't have a final review here. What I want you to focus on in reviewing this is this notion of cycling within systems. that natural systems have nutrient cycles which try to kind of optimize the extent to which the system is closed. In agri-ecosystems, there's increased opportunities for loss, either from leaching or from other processes. And that in conventional agriculture, the normal approach is just to apply more of the nutrients and worry less about closing the cycle. In more sustainable agri-ecosystems, the focus is on closing the cycle, trying to find ways to have a system that balances inputs and outputs so we don't have losses and we minimize the need for inputs. Thanks, and don't forget to check out the quiz on As You Learn. Thank you.